problem, we're going to pick the statement that best describes the relationship between each pair of molecules. Are they enantiomers, diastereomers, or molecules that are not stereoisomers at all? So when I look at D-ribose and L-ribose, okay, they're both ribose. The D and the L is distinguishing the enantiomers one from another. So D means that the bottommost hydroxide group is going to be on the right, and then the L means it's the mirror image, and that bottommost hydroxide is going to be on the left-hand side. So this is for glucose, L-glucose, and D-glucose. The same is going to be true for D and L anything. This bottom hydroxide is on the right, so that's the D enantiomer. Here the bottom hydroxide is on the left, so it's the L enantiomer. So looking at that bottom, that last hydroxide attached to a chiral carbon. You don't have to worry about these guys. These bottom ones over here are not chiral. This is a chiral carbon. This is a chiral carbon. So for D-ribose and L-ribose, the D and L means that they are enantiomers. They are non-superimposable mirror images of each other. So without even seeing the picture, I can say that that's true. Now, for D-glucose and D-galactose, we probably need a picture. Here is D-glucose, here is D-galactose, and if you look at them, we can try to find some differences. So they both have an aldehyde on top. They have hydroxide on the right here, and then on the left, they both have right, left. And then this one, glucose has one on the right-hand side. This is where they're different. They're different right here in that one space. Everything else is going to be the same. So glucose is right, left, right, right, and galactose is right, left, right. So they have the same number of carbons. They're definitely stereoisomers. They have the same number of carbons and hydrogens and oxygens. The connectivity is the same. The bonding is the same. The only thing that's different is which side that OH is on. Yeah. So those are called diastereomers. They are not mirror images of each other. They are, the stereoisomers. How about L-glucose and D-galactose? Let's look at those two. All right, so here's L-glucose and there's the galactose. So again, if D-glucose and D-galactose are diastereomers, then L-glucose and D-galactose are also going to be diastereomers. So you can see here, let's see, there's our L-glucose and D-galactose. They differ here, they're different here. These are the same, they're different. So they're different in a couple spots. But they are not mirror images of each other. So they are also diastereomers. And the last one, D-glucose and D2-deoxyribose. So the deoxyribose part, what does that even mean? On carbon 2 here, we lost an OH. So ribose has OH, all 3 hydroxides going down here. Deoxy means I lost one of the oxygens. So that's what happened there. I no longer have an oxygen there. But glucose, how many carbons does glucose have? 1, 2, 3, 4, 5, 6. And ribose has 1, D2-deoxyribose has 1, 2, 3, 4, 5. So they don't even have the same number of carbons. So they're not going to have the same molecular formula. They're not isomers at all. There we go. So if it's a D and L and they have the same name, same sugar, they're going to be enantiomers. Diastereomers are going to be things that have, that are not mirror images of each other, but still have the same number of carbons, hydrogens, oxygens. And then if they have a different number of carbons, hydrogens, oxygens, they're going to be not stereoisomers at all.